All right, everyone, welcome to today's Midday Science Cafe. We are so excited to have you. Thanks for waiting as we allowed folks to join. We have outer space's hottest and brightest objects, so stay tuned. I hope you guys are as excited as I am for this September Midday Science Cafe. I am going to do like I always do and start with a land acknowledgement. So please allow me the chance to just take a minute to recognize that Berkeley sits on the Huchun territory, the ancestral and unceded land of the Ohlone people, the successors of the historic and sovereign Verona Band of Alameda County. This land was and continues to be of great importance to the Ohlone tribe and other familial descendants of the Verona Band. Every member of the Berkeley community has and continues to benefit from the use and the occupation of this land since the institution's founding in 1868. By offering this land acknowledgement, the Berkeley community not only recognizes the history of the land on which we stand, but also recognizes that the Ohlone people are alive and flourishing members of the Berkeley and broader Bay Area communities today. So thank you again for allowing me to make that land acknowledgement. We're excited to be here today, but we also have some upcoming fall programming for you. We want you to know about. All About Animals will take place in October, and the Road to Vehicle Electrification, which is timely given the recent news, that will take place in November. These events are the third Thursday of every month, and they are always at noon. So I hope that this isn't your first time with us, but if it is, join us again. So I am the executive director of a program called Science at Cal, which is half of the program that you see here today, making up of the folks who organize this event. In 2008, Science at Cal was envisioned as a unifying effort to raise public awareness, understanding, and appreciation of scientific research at Berkeley. To realize this vision, we engage the vast Berkeley science, technology, engineering, and mathematics community as communicators, and we foster creative collaboration amongst campus, and community-based groups who share our commitment to equity and inclusion in STEM education and STEM careers. Science at Cal connects UC Berkeley researchers with the diverse community groups of all ages and backgrounds for science engagement and learning. Accessibility, inclusiveness, creativity, and innovations are hallmarks of Science at Cal events, which reach tens of thousands of people annually. Throughout the year, Science at Cal presents these ongoing and free programs in STEM and in other disciplines to help promote other groups' related efforts across campus. And we create programs and initiatives at Berkeley and in the community. This broad scope of activities is made possible by Science at Cal's dynamic network of campus alliances and valuable partners who I have up here, and all of our different kinds of events. We have a really big announcement. Our grad student specific early career researcher program called Grounds for Science, that is in person, is back at Caffeinated Coffee Company. We are on the first Tuesday of every month. We'll be there at 5:30 p.m. And similar to this program, we have 2 speakers that give presentations. So we're super excited to be back and in person. If you follow Science at Cal, you know that besides this program, all the rest of our programs are in person. So we hope to see you at our events, but we needed to take a moment to make that announcement because we're so excited to be back, in addition to the other 2 programs that we run in person during the month as well. And I just wanted, before I hand things over to Jen Tang from Berkeley Lab, I want to know, if you haven't already realized, this event is being recorded, and we will be posting it to both of our YouTube channels, so you can get a hold of this video after, watch it again, share it with your friends and family and your colleagues. In addition, you can there are live captioning options for you to get some captions if you need them and if you'd like them. And I want to also mention that we will be doing robust Q&A throughout this event, and you can always ask questions to any of the people you see on your screen today. And you can add those to the chat, or you can add them to the Q&A box. You don't have to add them to both. One is fine, and we'll be organizing those questions for our presenters. Now is my chance to hand things over to Jen Tang from Berkeley Lab.
Thank you so much, Dee. Hi, folks. So I am the Director of Community Relations at Berkeley Lab. And as I usually do, I'm going to talk a little bit about the lab for those folks who aren't familiar. As you may or may not know, we are one of 17 U.S. Department of Energy national laboratories across the country. And we are supported by the Department of Energy's Office of Science and managed by the University of California. All of the science we conduct at the lab is unclassified. And since our founding in 1931 by a UC Berkeley professor named Ernest Orlando Lawrence, we have been dedicated to, I think so, I was like, uh-oh, Dee. We've been dedicated to advancing the scope of human knowledge and seeking answers to some of the greatest problems facing humankind. And today, Berkeley Lab employees work together to develop meaningful scientific solutions to the world's most intractable energy and environmental challenges. We help train the next generation of scientists and engineers, and we work hard to ensure that those things happen in a manner that benefits everyone. Our main campus is located in the Berkeley Hills, and our close ties to the UC system create a really unique and synergistic environment for scientific discovery. And a number of the lab's researchers are affiliated with one of the UC campuses, either as students, postdocs, or professors who have a joint appointment at the lab. And we are very fortunate to have a close relationship with UC Berkeley, and our institutions have joined forces to advance science across a number of different frontiers. And as you know, one of the main motivations for creating Midday Science Cafe is to share with you examples of those compelling and complementary scientific research projects from both our institutions. So we hope you enjoy today's presentation. All right, Dee, thanks so much. Back over to you.
Thank you. So I'm going to stop share and I'm going to invite our first speaker, Stephen Giacalone. He's in his final year of his PhD at UC Berkeley Department of Astronomy. His research focuses on searching for planets outside of the solar system by looking for periodic dips in the brightness of distant stars, a signal that implies that there are planets orbiting those stars. Using this method, Stephen learns about the demographics of planets throughout the galaxy. His thesis focuses on determining how common planets are around A-type stars, which we'll learn about today, which are hot stars about twice as large as our sun, to infer if planets form and evolve differently around them compared to stars that are more like our sun. Stephen grew up in Long Island, New York, and he attended college in Chicago, Illinois, before moving to Berkeley and joining Berkeley for grad school. Outside of his work, Stephen enjoys spending the weekends hiking, camping, and surfing around the Bay Area. He also organizes a monthly outreach event called Astro Night, which Science at Cal often helps promote. So if you're on our listserv, again, there's another plug to join our listserv and stay tuned on our social medias. This is a night where local scientists give public lectures about their research on evenings with clear skies. The events also involve stargazing sessions on the top floor of the balcony at the Department of Astronomy with several of our many telescopes. We will add the info about Astro Nights in the chat for you, Stephen. So without further ado, I'm so excited to have you here today. Take it away.
Thank you, Dee, and thank you for the Astro Night plug as well. So yeah, thanks for giving me an opportunity to talk today about my research. I'm going to be talking a little bit about planets, a little bit about sunscreen, and how those two relate. So I'm going to start off really basic with the sunscreen part. So sure, a lot of people here wear sunscreen. You should wear sunscreen if you don't. So sunscreen, so the basics are the sun emits very high energy ultraviolet radiation. This radiation can cause damage to our skin cells, which can manifest as sunburn, aging, and in unfortunate cases, cancer. So sunscreen essentially absorbs the ultraviolet radiation before it can get into our skin, and so it prevents damage to our skin. Now, to understand a little bit what ultraviolet radiation is, I'm going to talk about a spectrum of the sun here. So this is a plot showing how much light the sun emits as a function of the wavelength of the light, or equivalently the color of the light. So there are three different regimes that I'm going to just sort of walk through here. On the right side, we have infrared light. In the middle, we have visible light. So this is the light that we see, the sort of rainbow of colors that we're all familiar with. And on the left, we have ultraviolet light. So ultraviolet light is the highest energy and the shortest wavelength of all the lights here. So that was a spectrum as we would see the sun from space, but if we were to take a spectrum of the sun from Earth, it would actually look a little bit different. And now it would look like this new dark curve that's plotted here. And you'll notice that there are a couple of interesting features that make this different from the spectrum from space. And in particular, there are these three big dips that you can see. These are actually absorption features. So as light from the sun goes through the Earth's atmosphere on its way to us on the surface, different molecules and elements in the atmosphere absorb that light, and so it can't reach us. So on the right, we have a big dip here from H2O, from water. Then we have another big dip from O2, which is free oxygen. And then all the way to the left under ultraviolet, we have a bit of a drop off here from O3. Now, another word for O3 is actually ozone. So people have probably heard of ozone and the ozone layer. So the reason why the ozone layer is so important is because it absorbs a lot of ultraviolet light and therefore protects us from the harmful effects of the sun. So maintaining the ozone layer is super important for making sure that us and all other animals on Earth are happy and healthy. Okay, so we saw here that the atmosphere of the Earth specifically protects us from the harmful effects of the sun, but you can't help but wonder what happens to the atmosphere. Are these high energy photons, this high energy light, also harmful to the atmospheres of planets? And to answer this question, I study something called exoplanets. So here I have a diagram of the solar system. You have the sun in the middle and the 8 planets that we all know and love. Here's Earth, this little blue one. So exoplanets are planets in extrasolar systems. So extrasolar just meaning outside of the sun, essentially. So these are stars that are not the sun with planets orbiting around them, also known as exoplanets. So if I use the term exoplanets, this is what I'm referring to. We know, based on studies of exoplanets, that those orbiting very close to their stars can have their entire atmosphere stripped away due to high energy radiation. But we don't actually know right now how efficient this stripping is or how destructive the high energy radiation is in a quantifiable way. And consequently, we don't really know how high energy radiation affects the habitability of planets. So we can ask the question is, can all planets protect life from ultraviolet radiation in a similar way that the Earth does for us? So now I'm going to talk about the specific types of planets that I study to do this work. So here's another diagram of the solar system, just the inner part out to Earth. The sizes of the planets are not to scale here, but the distances between them are roughly to scale. So we all know that Mercury is the closest planet to the sun in the solar system, but in extrasolar systems, there are actually planets orbiting much closer to their stars within the orbit of Mercury. So first of all, yeah, I study planets that orbit very, very close to their stars. The second thing to note is that I study pretty big planets. So planets roughly the size of Neptune to the size of Saturn. These are mostly gassy planets like the gas giants in the solar system. And so we're talking about a context where we're not talking about a solid surface like the Earth, we're talking about big balls of gas, essentially. And the third distinction I have to make is that I don't study planets around sun-like stars, I study planets around A-type stars. Dee talked a little bit about this in my introduction, but A-type stars are about twice as big as the sun and are almost twice as hot. And as a consequence of that, they emit a lot more light in the ultraviolet than the sun does. So to sort of visualize how much ultraviolet light A-type stars emit, I'm going to show a little animation here. So here's the spectrum from before of the sun as viewed from space. And I'm going to click go, and the y-axis is going to change, and you're going to see how much more light is emitted by A-type stars because they're so much hotter. Okay, so the spectrum of the sun is going down, everything's being squished, and coming into frame is the spectrum of an A-type star. So it's pretty big, pretty scary. It's brighter in general because hotter stars are brighter, but also it emits a lot more light in the ultraviolet. So you'll see where the sun sort of drops off between about 200 and 300 nanometers. A-type stars go all the way out to like 100 nanometers. So this is a lot of very high energy radiation that any planet orbiting an A-type star is going to be subjected to. So how do I do it? How do I actually study these planets? I use a space telescope called the Transiting Exoplanet Survey Satellite, or TESS for short. which searches for planets around the 10 million brightest stars in the sky. And because we have such a big sample of stars, we can use this data to do demographic studies to determine what kinds of planets orbit different types of stars, and from there back out the evolutions of planets in those systems. So just as an example of what kind of data we're talking about, this is an image or part of an image taken from TESS during its commissioning. So TESS has 4 cameras and each camera has 4 chips. And this is one image from a single chip. So this is a 16th of a full image that TESS takes. So you can see there are hundreds or thousands of stars you can see here. There are even more that you can't see just because the contrast. So we're talking about a lot of stars that are being viewed at a single time. So specifically what I do with TESS data is I want to map out a planetary desert. So that'll make a little bit more sense in a second, but let me explain what exactly I'm doing. So I look at A-type stars and I look for planets around those stars. So I'll start very close to the star at a certain distance and I'll look for planets. And if I don't find any planets, then you can pretty much conclude that, well, there aren't any planets there, they must be really rare. Then you move out to another distance and you do the same exercise. And maybe you'll again conclude that I'm not finding any planets, and so they have to be really rare here. And you keep doing that until you get to a distance where you actually start finding planets. You actually start finding, in my case, specifically these sort of Neptune-sized planets. And so what that tells us is how close a planet can get to an A-type star before its atmosphere is completely stripped away. Because once the atmosphere is stripped away, all you're left with is a really tiny core that's actually so tiny that we can't detect it. And so we've learned a few interesting things through this research so far. First of all, Neptune-sized planets close to A-type stars have their atmospheres fully stripped away due to high energy radiation, leaving only those tiny cores that we can't find. And this actually allows us to quantify how destructive ultraviolet radiation is for planet atmospheres, which is a really important first step in determining how planets around different types of stars form and evolve. But there are still a lot of questions that we don't know. So for example, how does the high energy radiation of these stars affect the habitability of the planets orbiting them? And more specifically, can Earth-like planets protect life from such high energies of ultraviolet radiation in a similar way that the Earth does for us? And so I want to leave you with a sort of fun reminder. A lot of the things I've been talking about today might seem a little abstract. Like I talked about A-type stars. A lot of people probably haven't heard that term before. But I want to let you know that A-type stars are actually some of the brightest stars in the night sky. So every time you look up at night, you're probably seeing an A-type star. One example is the summer triangle. So the summer triangle is visible now, actually. If you go out after sunset, when it gets dark, assuming there are no clouds, you'll see 3 bright stars in a triangular formation. These are Vega, Altair, and Deneb. These are all A-type stars, 3 of the, I think, top 10 list of brightest stars in the night sky. And another example of an A-type star that you can see at night is in the winter triangle. So this is visible in the winter and spring. The winter triangle is made of 3 stars, Procyon, Betelgeuse, and Sirius. Procyon and Betelgeuse aren't A-type stars, but Sirius is an A-type star. And Sirius happens to be the brightest star in the night sky. So these are stars that anyone can see without a telescope anytime they go out at night. And if you want to find the winter triangle, it's really close to Orion, which I think a lot of people recognize. So yeah, so hopefully I leave you with the reminder that you look up at the night sky and maybe try to imagine what planets around these really bright A-type stars might look like, and specifically whether or not planets around these stars could benefit from using sunscreen like we do.
Thank you so much. That was wonderful, Stephen. We are going to take a few questions from the audience before we hand things over to Jen and Satya. So first question, what even determines whether or not a planet is habitable?
Yeah,
How do you know?
That's a good question. So determining if a planet's habitable, it's still a pretty relatively young field, and there are a lot of factors that can go into it. So typically the way astronomers think about habitability now is we want to look for planets in what we call the habitable zone, which is a distance from a star that is warm enough for water to be liquid, but not so warm and not so cold that it evaporates or freezes. But there are, of course, a lot of other ways that we think life could exist. So for example, like icy moons of Jupiter and Saturn, which have subsurface oceans, we think that possibly life could form and evolve on those planets as well. And so it's a really complex sort of area of study, but hopefully within the next few decades, we'll get a better understanding of it with these new space missions.
Great. So we had one clarifying question too. So can you go over again about whether or not the sun is an A-type star? Could you specify that?
Yeah, I think I missed the first part of the question.
Oh, just that somebody wanted clarity on whether or not the sun is an A-type star or not, and what makes an A-type star. Again,
Gotcha.
Yeah.
So the sun is not an A-type star. The sun is about half as massive and half as big as A-type stars.
Okay.
Yeah, so when stars form, they have sort of that initial mass, and the initial mass of the star determines how hot it's going to be. So A-type stars start a lot more massive, and so they get bigger and they get hotter than sun-like stars.
Oh, interesting. Okay, so they don't change sizes necessarily?
Eventually stars will, as they become like red giants and stuff, and I'm sure people have heard those terms. But I'm thinking mainly about stars in the on the main sequence, which is like the sort of main
average star.
Yeah, the average star.
The average star. All right, perfect. Thanks so much, Stephen. We have a ton more questions for you when we get back to the Q&A. So why don't you go ahead? Yes, stop share, and I will hand things over to Jen. Thank you.
Awesome. Thanks so much. And Stephen, that was a great presentation. And it is now my pleasure to invite our next speaker to the screen, Dr. Satya Gontcho A Gontcho. And Satya is a French cosmologist who's working at the forefront of the efforts to build the largest three-dimensional map of the observable universe ever made by mankind. She received her PhD from the University of Barcelona and worked at the University College London and the University of Rochester before joining Berkeley Lab as a project scientist. Her work studying the distribution of matter in the universe in the era following the formation of the first stars and galaxies earned her a spot on Forbes's 30 Under 30 list in 2019. That same year, she was a recipient of the Giuseppe Siaca International Award in Acknowledgement for her scientific excellence and her strong commitment to mentor future generations of scientists. In her spare time, Satya uses her experience as a scientist and as a performance artist to explore the various ways that storytelling can be adapted to reach a broad audience and bring the public's attention to the wonder of understanding the universe in which we live. Satya, over to you.
Thank you very much. So hello, everyone. And first of all, thank you to the Midday Science Cafe for inviting me to talk to you today. I'm also super pleased to be back in Berkeley because I actually did one of my very first internship 10 years ago on campus when I was a master's student. So it's really fun. So today I'm going to tell you about how we can use quasars that are the most luminous objects in the universe to create and map out the universe. And so who says mapping out the universe wants to answer a question that is what is in the universe and then where is it? And these on screen you can see are the proportions of the three components that make up the content of the universe today. So we have dark energy, that's about 70%, dark matter, that's 25%, and ordinary matter, that's about 5%. And for today, we're only going to focus on those about 30% and all the matter components, dark matter and ordinary matter. And as a starting point, we're going to remember that dark matter does not emit any light. It's very heavy. And the only way that we know that it exists is just we see its mass act on everything around it. Good. But then when we're considering ordinary matter, that in the end is only about 5% of everything that's in the universe, we're going to split it into two categories, right? Ordinary matter is what you and I are made of, but also what stars and galaxies are made of, and as well what cold gas, the gas that is between galaxies, is made of. And I'm splitting galaxies and stars from the gas because galaxies and stars shine. They emit light, you can see them. But the gas, for example, hydrogen gas, it doesn't emit any light. So it doesn't shine anything at you. And so if you were to look up at the sky like this, what you would see is exactly, if we're taking a picture with a really good camera, you see the light coming from the stars and from the galaxies. And this is real astronomical data. You have a URL at the bottom. It's actually a survey that I'm a part of, and all the data are public. So if you want to go and play with the real astronomical data, you can. And now, when you're looking at this picture, this normal 2D image, we're only on Earth. So this is the only point of view that we can take pictures from for the universe. Even, satellites, we don't go much further. And so how can we, from this 2D image, reconstruct then a 3D map? Well, it's one of the greatest difficulty of astronomy, but also what makes the cornerstone of our field is that we have learned how to measure distances in the universe and understanding how things are, how far away they are from us just by looking at their light. And so if you look at this image and you apply that knowledge, you'll see that, let's say that we identified the closest galaxies to us in red, circled here, and then we identify galaxies that are a little bit further away, and then again further away, and then again further away. What happens is, just as a detective that would be putting clues collected together in the right order, and then using perspective to extract information from its clues, we're able to use the 2D images of the sky to divide it into different slices of different depth, and then we create a 3D reconstruction of that part of the sky. But, again, we're using things that we can see. So let's say now that you're using a light bulb and you're moving that light bulb away from you. And as you move it away from you, it's going to be harder to see. And that makes sense. And so if you wanted to still look very far away, but still see your light bulb, you might want to consider switching it for a lighthouse. It's a lot more powerful. And then, at big distances, then you would still see the lighthouse much better than you would see the light bulb. And that analogy, it's a little bit the difference between galaxies and quasars, because galaxies are dimmer than quasars. Quasars are really the most luminous, the brightest objects that we have in the universe. And so when we're building, this 3D map, which is basically we want to know where things are by looking at them, we can reconstruct the map close to us by looking at galaxies. But then as we go deeper, it becomes harder to see galaxies. So we have no other choice than to look at the only thing that's shining at us and that we can easily look at. And these are quasars. We're using them as our beacon. Now, I'm going to tell you a little bit more about quasars. And I stated already that they're the brightest objects in the universe. But what else do you need to know? Well, at their center, there is a supermassive black hole that pulls towards it any ordinary matter that's lying around. And just like in your kitchen drain, for example, all that matter is going to start spinning really fast around the supermassive black hole. That's what you're seeing here. And then it's going to bump into other fast-moving matter, right? There's friction. And so things heat up and energy is going to be released in the form of light. And that culminates close to the center in those two jets that you're seeing here. That is bright hot matter that's ejected on each side of the supermassive black hole. Now, the reason I'm pointing this out is because the dynamics and the way that the energy is released is so particular that the light that quasars shine goes over the entire spectrum of light. So Steve already introduced, the term of infrared, visible, ultraviolet light. And so quasars emit in all these lights, in all these colors. And now you may wonder, but do they emit as much, UV light as infrared light? Well, not quite. Actually, most of the light that quasars release is in the ultraviolet, and specifically at a wavelength that's called 1216 angstrom. And the reason I'm telling you about this wavelength is because it has a significance when it comes to the atom of hydrogen. And so as it turns out, when you're considering the ordinary matter that's in the universe, hydrogen is the most common element that you can find everywhere. And if you have hydrogen everywhere, and the light of your quasar is shown at a color that is very significant and has interactions with atom of hydrogen, then you can guess that as the light travels in the universe, the light of these quasars, they're going to have a lot of chances to interact with clouds of neutral hydrogen. And in the same way that you have the light from the sun that's coming through the clouds in our atmosphere, the light of the sun is going to be changed, just as simple as being dimmed because it goes through the clouds and it interacts with them. Well, for the light of the quasars, it's very similar. It's going to cross a cloud of, neutral hydrogen. So, a cloud hanging out in between galaxies. And all the light that is the 1216 angstrom color is going to be affected, is going to be changed by the fact that it crossed that hydrogen cloud. And so something else of note is a cloud of neutral hydrogen, all this matter that's laying around in between galaxies, that's not stars or galaxies or quasars, it doesn't emit any light. And so you can't see them on their own. You need to shine something through them to then become aware that they're around. And so that's why we think quasars as well. And again, they're very bright, so you can see them from very far away. So you're covering a lot of ground. And they used to be more abundant in the early universe than they are now, which means we see more of them the further away that we look. Now, something that I haven't mentioned just yet is also that the universe is in expansion. And so space between two places in the universe is always growing. And the light travels at a finite speed. It may be very fast, but it's not instantaneous. And so that means that when the light of a quasar, travels towards us, it's going to take time to get there. But as it travels, space keeps increasing. And so it has a lot more distance to cross in order to reach us. And what you're seeing in that cartoon here is that, something that's very close, the wavelength, so the colors are going to be in a certain way, but then if it's further away, because it has so much effort and so much more space to cover, then the wavelength gets stretched. And, the further you go, the more that phenomenon happens. And another way to phrase it is that what was ultraviolet light before, if it's very far away, as it travels to us, it's going to become infrared, and so on. And so the colors of the light gets shifted towards redder colors, and that phenomenon is called redshift. And again, I'm going to show you, just like we have seen spectrum of stars before, now I'm going to show you a spectrum of a quasar. And on the horizontal axis, you have a wavelength, but that just means a color. And here you have how much light of that color do I have? And what happens as it travels is, blue becomes red, becomes green, becomes red. Everything is shifted. Now, looking at this little video, it's a quasar spectra, and then on top, you'll see the light moving through a universe that has those gas clouds. And as you can see, what happens is the whole spectra, the colors, everything's shifted towards the right, towards redder wavelength, but also as it travels through the clouds of hydrogen gas, it interacts with it. And you can see that we had a lot of light, and now at certain places, we have less light. It gets dimmer, we have absorption features. And a little bit qualitatively, basically the bigger, the thicker the cloud that you go through, the stronger this diminution, this absorption feature. And I've shown you that for one quasar, but I said there's many, many, many quasars in the universe, right? If we're here and, on the other end, we have those quasars, and in between you have a lot of gas. And so for each of those lines, then you're able to look at the spectrum and say, oh, I see now there's a dip, there's a dip, there's another dip. And you're able to place those dips with, oh, that means there is a cloud that is this thick here and this thick here. And if that purple haze that you're seeing here is where the gas is distributed. You shine quasar light at it and it illuminates it so that now from Earth, we couldn't see that gas before, but now we can. And so that's really why quasars are so cool, is that they allow us to highlight ordinary matter that doesn't shine and that otherwise we could not see. And because they're so bright and that we can see them from very far away, they will highlight this matter that doesn't shine from very far away. And now I'm just gonna, leave you with that idea that we are trying to build a large 3D map. So if we're here and we're doing a sweep of the sky, we're looking deeper and deeper and deeper. And what's white here is the galaxies, because, they're close and we can see them. But as we go further and further away, all those red dots, let's say they're quasars and there's the gas, and that's the information you're recovering. Now, I'm gonna, play that little GIF, and it's a sweep of the sky. And basically you're seeing, it's not homogeneous, right? You're seeing substructures. And that's the map and the structure that you're trying to look at. And I want to highlight that this is, again, real data that has been taken in the past year with something called the Dark Energy Spectroscopic Instrument. And it's a major cosmological survey that Berkeley Lab is in charge of leading, and that has already built, but by the next 5 years, will have built an even bigger 3D map, and so far the largest 3D map of the observable universe in existence. And so we thank quasars for allowing us to, get to the deeper part of that map. So thank you so much, and I'll take your questions.
Wonderful. Thanks so much, Satya. That was a great presentation. So we've got a couple questions we want to ask you before we bring Dee and Stephen back to the screen. So first, can galaxies be used to shine light on gas the same way that we use quasars to do that?
That's a really good question. Yes, they can be used to shine light on cold gas. Now, because they're closer and because galaxies are, very complex astronomical objects, and they don't all shine in the same way. Whereas something I haven't mentioned is quasars all shine in a kind of standard way. We can definitely identify features and use them to help us understand what's in between the galaxy and us, but it's not as clear-cut and evident as what we're seeing in quasars because they shine differently.
Got it. Fascinating. Okay, so one more question, and maybe this is, you could tell this is a non-scientist asking. Aside from the fact that it's just really awesome, is there any reason why we're trying to make the largest 3D map of the universe, and what are we learning from it?
Yes. So, the first instinct of a human might be to just want to explore and see things because they're cool and we want to just map out. But then what's really nice about creating that 3D map is we were saying that light takes time to travel. And so whatever you're seeing very deep in that map, it's actually outdated. And as you're building, this 3D map, the deeper you go into it, you're also kind of going back in time because that information is old. And so you can, as you make your slices of, depth, meaning for a certain depth, I'm going at a certain period back in time. If you have, you make slices and slices and slices of different depth and different moment in time, then you just get images one after the other in chronological order. And that's called a GIF if you have very few images. And if you have a lot of images, that's called a movie. And so that way we're able to actually see and understand and have access to understand what happened chronologically and what took place in the evolution of our universe. So that's the reason that we're building this 3D map.
Got it. Awesome. Well, thank you so much. So what I'm going to ask you to do now is stop sharing your screen, and I'm going to invite Stephen and Dee back to the stage, the virtual stage with us, and we'll get started with our general Q&A session. Okay, and maybe Dee, I'll hand things off to you for the first couple questions.
Yeah, here's one I really like because I hadn't thought about it. How do you know whether an exoplanet is rocky or gaseous?
Yeah, so this is something that we learned in part with TESS. So essentially, the way that TESS looks for planets is it waits for the planet to go in front of the star. And when you measure the difference in brightness from when the planet is in front of the star versus not in front of the star, you can calculate the size of the planet. Through a different method called the radial velocity method, you can get the mass of the planet. And so when you have the mass and the size of the planet, you can calculate the bulk density because it's mass over volume. And so it turns out that if you plot the density of exoplanets as a function of their size, so density on the y-axis, size on the x-axis, and you start with like Earth size, and you start to go to bigger planets, there's a big jump around planets 1.5 times the size of Earth, where at that boundary, planets become much less dense. And so what that tells us is that around that radius, planets start to accumulate big gassy atmospheres, kind of like Neptune. And below that radius, you can have planets that are rocky, that have very thin atmospheres like the Earth and like Venus, for example.
That's very interesting. So there's like a threshold and a cutoff that naturally forms. Very cool. So if stars hotter than the sun emit more ultraviolet radiation, why don't we just look for habitable planets around stars that are cooler than the sun that emit less ultraviolet radiation because they're cooler?
Yeah, so I actually saw another another question related to this. So there are a lot of people, including my advisor, that their research focuses on looking for planets around smaller, cooler stars like M-type stars. So there are people trying to study the habitability of these planets, but one of the issues with planets orbiting these types of stars is that with the very small, cool stars, they're actually very active in that they emit a lot of X-rays and they have a lot of like stellar flares, which can be problematic for the atmospheres and for life on the planets for a whole different reason from the ultraviolet radiation that A-type stars emit. So I would not be surprised if in the future we find out that sun-like stars really are a sweet spot between A-type stars that emit a lot of ultraviolet radiation and M-type stars that emit a lot of X-rays and stellar flares. So yeah, sun-like stars might be the sweet spot where it's most hospitable for life.
Was the question the red dwarf M stars emitting violent solar storms question?
Yeah.
Okay, I'll repeat that question and let you answer that if you have anything more. So supposedly red dwarf M stars can emit violent solar storms impacting their close in potentially habitable planets. Do A-type stars behave more than the M dwarfs? So you can explain that question and answer.
Yeah. So for people that don't know the terms, so there are sun-like stars, which are called G-type stars. And then if you go to very low mass, very cool stars, they're called M-type stars, also called red dwarfs, if you heard that term. And then if you go to hotter and more massive stars, you eventually get to A-type stars. So it turns out that M-type stars and A-type stars are both kind of bad for life, but for different reasons. So, and the reasoning, the reason why they're both bad, well, the reason why they're different, it comes down to the properties of the star themselves. So M-type stars, these very cool stars, have convective interiors. So convection is sort of like when water boils, you have like a bulk cycling of material. And when you have that, you get a lot of magnetic activity. And the magnetic activity causes solar flares and causes X-ray emission, essentially. A-type stars, on the other hand, don't have any convection. They're just completely radiative on the inside. So energy is just transported by light that's traveling from the center of the star to the exterior of the star. And so they don't have any magnetic activity. And so they don't have flares or X-rays, but because they're so hot, they emit so much near ultraviolet light, just like natively, right? And so I wouldn't say that A-type stars behave more than M-type stars. I think that they're both kind of bad for life, but for different reasons.
I love that. And I love the behave and the bad and the good. It's like really helping us kind of pull life out of this research. So it's so neat to hear folks so interested in it and knowing quite a lot. So I'm going to hand things to Jen. She can ask a few questions.
Awesome. Thanks so much. So I've got a bunch of questions for Satya about quasars. I'm going to throw them all at you. Let me know if you need me to repeat them. But the first is, how do quasars form? And why are there so many of them? How long do they live? How large is a quasar in comparison to a galaxy? I think we just want to know a little bit more about what these mysterious quasars are.
So when the universe was younger, we just, we had this soup of everything, and then the universe expands, and all of those gas, all of those particles start falling where you have dark matter. They start getting settling where you have more gravity, more weight pulling them. And as you have things that start bumping into each other and settling, that's how the first stars are formed, right? You have matter bumping into each other and creating nuclear reaction and these first stars. But then they keep, stars then start, getting closer and closer together, and then that forms galaxies, and you get to bigger and bigger structures. But you also have some configurations where what bumps into each other is so close together and in such a small radius that a black hole will form. And if it happens in an environment where you have a lot of gas or stuff laying around, enough so that it makes for a huge black hole with, you have black holes of different masses. But if it's really a bigger mass than the other black holes, then you will also have, just like I was saying, the drain, right, in your kitchen, things start falling towards that black hole. And because there's friction in between all of that stuff, all of that gas, that will create, when you have too much energy, one way that you have to get rid of it, an excess of energy, is to emit light. And so really that's the basic mechanism of how quasars are formed. And because early on in the universe, everything was, the structures were not as defined, so you have a bunch of stuff everywhere. So you had a lot of these phenomena happening. Now we are in big structures, right? We have the Earth and the solar system and our galaxies and other galaxies. And now things are actually very far away from each other. You just have like dots everywhere, quite far away from each other, a little gas, but not as close for interactions. So you don't have the conditions to have new quasars forming just as much as you had when the universe was younger. So that's one thing. And as far as the lifetime of a quasar, that's actually, at least to the best of my knowledge, is still a very much active research question, because I don't know that anyone has yet observed the end of the life of a quasar. And so whenever we make models, we're always like, well, we can put, life of quasar infinite or, longer than what we've seen so far. That's a big, big question mark.
Fascinating. Thanks for those answers. So you had mentioned that black holes take in ordinary matter. Is there a reason why dark matter doesn't also go into the black holes?
So I mentioned when things get pulled together, they bump into each other. And one of the reasons that they bump and that they emit light and that there's friction, it's not because of gravity. Gravity is what brings them together. But then the same reason that you can touch the table is actually not gravity, it's electromagnetic force, right? There's a reaction. And dark matter does not submit or to electromagnetic force. The only force that it responds to is gravity. And so the black hole is going to pull dark matter, sure. But then when dark matter meets dark matter, they just pass through. And so that's the reason that it doesn't contribute to the dynamic and of formation of a black hole in the same way that ordinary matter would.
Got it. Thanks so much. So a couple questions about the dark energy spectroscopic instrument and the images it's taking. how can you compare those images to the ones that are being taken from space, like the images that the James Webb Space Telescope is taking right now?
Yes. So first of all, James Webb is just giving us, a lot of eye candy that everyone's very excited to look at. So it's really awesome. One big difference between being in space and being on the ground is we have the atmosphere on the ground. So we have clouds, we have a lot of things that we need to account for. So we just have already clearer and less noise when we're in space. One difference, though, is you can only bring smaller things into space, right? When you're traveling, you pack light. When you're staying put and at home, you have a lot bigger equipments. And so James Webb has amazing quality. But if I was to say, it looks at fields of views like that. It's a very, very tiny camera. It's very precise. What we do from Earth is we have huge cameras, so we can look at, a lot bigger field of views, but just with less quality. Now, how it compares to the dark energy spectroscopic instrument that you mentioned is, for us, we're not taking regular pictures. Instead, we use regular pictures to say, oh, this is where all the galaxies that we want to look at are. Now let us point not a camera, but more a fiber, a fiber optic, just like the one that's bringing you internet. And let us get all the photons coming from just that one galaxy that now we know very precisely where to point. And let's count how many photons of which color we have. And this gives us a way to measure the distance of that galaxy much better than if we were using a regular picture. And so that's what we're using to make a very precise 3D map of the universe.
Got it. Thanks for that explanation. All right, I'm going to hand things back over to Dee.
There's lots of good tidbits of trivia in all of those responses, Satya. That was great. So Stephen, what's the time frame for a planet being stripped of its to its core by an A-type star? That's also a really great question.
Yeah, so the short answer is we don't know yet. So the research that I'm doing is the first time that someone has actually tried to quantify this sort of stripping around A-type stars. What I can say is that we know how long A-type stars live. So A-type stars only live around 1 billion years, whereas the sun, for example, lives for 10 billion years. So it's about a tenth of the time span. So the stripping has to happen on the order of a few hundreds of millions of years, if not shorter than that. But beyond that, we don't actually know. But maybe in the future, there are people that study very young stars, like on the order of just millions of years old. So maybe in the future, we'll be able to learn about the timescale by studying those stars.
Yeah, so unlike quasars, we have kind of a theoretical framework which allows us to do those calculations.
Sorry, I couldn't, the audio.
I know my mic is being
halfway.
weird, I heard. I was just saying that we have a basis of a theoretical framework where we can make those calculations that we can't make with the quasars, right?
Oh yeah, for sure.
Yeah, because we haven't been around a billion years.
Yeah.
All right. So do you think we'll ever get to the point where we can look for signs of life on the surface of these planets? Something like the red-green transition of photosynthesis? How do you feel about kind of looking into the future?
Yeah, so this is something that people do think about. It's mostly a limitation right now of just the technology we have. So specifically, if you wanted to look for signs of plant life or photosynthesis, you would need to be looking at the reflected light from an Earth-sized planet, which is really, really hard to do right now. Maybe in a few decades, with new space telescopes, we'll be able to do that. But yeah, for people that don't know, for photosynthesis, there's something really cool that you can look at called the red edge. So we mostly think about plants as being green, and that's because in the visible light that we see, they reflect green light, they don't absorb it. But it turns out that if you were to go into the infrared where the human eye can't see, they reflect much, much more light than they do green light. So if we had eyes that could see across from the visible all the way through the infrared, plants would probably be like red because they reflect so much light. And so if you took a spectrum from the optical to the infrared of a planet that has plant life and has a largely photosynthetic surface, you would see this big jump in once you get to infrared wavelengths. It looks like a cliff. So people call that the photosynthetic red edge, because it's just like an edge that drops where the planets start absorbing light. So yeah, so we can't do that now, but in the future with new space telescopes, new instruments, that's something people will look for sure.
So all of these young scientists in the audience, potentially, you have something definitely very cool to look forward to for future work in this area. So here's a quick question. Are the rocky planets like Mercury and Mars, are those like the cores of the gas giants? So there's just the gas giants around these planets that look more like Mercury to Mars?
Yeah, so that's another thing that we don't really know. It's actually a rapidly evolving sort of field of what the cores of gas giants look like. So traditionally, what people used to think is that it was like a rocky core and then you just have gas around it. But now what people think through studying the solar system planets like Jupiter and Saturn is that you may have what they call a diffuse core. So you have it's gas, and then it slowly sort of converts to becoming like liquid solid, and it's like a gradient.
I
So
love
there's
that.
not a hard transition from core to gas, which of course complicates this whole like the whole atmospheric stripping thing, because how does that work physically? Like we don't know what it even looks like down there.
So more research to come.
Yeah, a lot of research.
You have a big we have a very bright future ahead of you too, Steve. Lots of things to look at. All right, I'm going to hand things over to Jen and Satya.
Thanks both. Okay, Satya. So you said that quasars can be used as a backlight. Does that mean it can illuminate everything around us, or just what's in a collinear line with us in the quasar?
So because I was saying they have those two jets that are going in two different directions, the amount of light that we're getting from quasars is not the same depending on which angle you're looking at them. However, they will emit light in all directions. They're just like a direction in which you will be blinded more than others. And so, however, we're in a little corner of the universe, so we always only see things from one point of view. And so what the information that we're learning by looking at how the light has changed, it's always on the way to us. And so that's why the information that we're getting is for what's in between the source of light and ourselves.
Got it. Okay. And besides, from the Doppler shift, are there differences in the emission spectrum of different quasars?
Again, this is a field of active study, but for now, there's no reason to believe that there are major differences. Again, it's standard. We say it's a standard candle or standardizable. The difference is either you're doing a copy paste or you're doing a copy paste that's slightly different, but close enough that you know how to, mold it back to having similar things that have similar shape. And so quasars, we understand that two very little differences, so little that for now, for us, it doesn't affect greatly the science that we're doing. They shine, we can start from the point of view that they shine exactly all in the same way. And we're already getting great science with that. And then if you start adding, actually they shine a little differently, let's add that into our calculations. We're seeing that it has a small effect, but it doesn't change the fundamental way the method work and the results that we're finding for now.
Got it. Okay. So let me ask you one more question about the James Webb Space Telescope. How do you think it will affect studies on quasars? One of our audience members heard that it would be able to go very far to the origin of the universe.
Absolutely. So to the origin, I wouldn't say so, but at least very, very much deeper than what we're able to do with ground-based surveys. And so, for example, with the project I'm a part of, all of the quasars that we're getting are, let's say, 11.3 billion years old, something like that. Now with James Webb, you're going, I think they announced that they found a quasar, which I'm going to misquote that number, but I want to say it's closer to like 12 or 12.5 or even 13 billion years old. And so you're just skipping, one full unit of billions of years, and you're having access to things that are much older. And so if you can see things that are much older, then you're learning about the universe and how it was at that stage. And so really, there's going to be a lot of exciting science coming from James Webb.
Awesome. One more question about the telescope, and then I'm going to ask Dee to ask some more questions. So does the James Webb telescope, does it just see infrared light, or is it a broader spectrum?
All right, I'm going to be candid. I know that it sees different wavelengths, more than just infrared. What these are, I have no idea because I don't work on it, and I can't remember off the top of my head, so I don't want to give a wrong answer.
Totally. No, that's okay. Thanks, Satya.
Steve, do you have any ideas? Or you don't work in that space either? Do you have any ideas, Stephen? Or do you not know either?
For the wavelength range of the James Webb?
Yeah. Mm-hmm.
So it is predominantly in the infrared.
Mm-hmm.
I think it goes out to, I don't know if this will make sense to people, but I think it goes out to something like about, I think it goes out to like 50 microns at most, which is sort of mid-infrared.
Mm-hmm.
And then I think it stops around like red in the optical.
Got it.
It's broad, but it covers a lot of the infrared, which we haven't had a telescope dedicated to do before, which is why it's so important.
Cool. Yeah, we were trying to figure out who could answer this. Probably both of them have some or a little bit, or yeah, so thank you. So I'm going to ask you questions about tests now, and we know that the audience knows a bit about it, and so it's great to have an expert here. So have you had results from tests where you haven't been able to explain the apparent dimming of an A-type star, but it's not an exoplanet?
For an A-type star,
how about any star? You could answer.
Not so much. Yeah, there are interesting. So A-type stars are somewhat simple. They don't have star spots like stars like the sun do. So they're pretty much just smooth. Sometimes they oscillate, so they'll like jiggle, and sometimes that can cause wiggles in their brightness. But other than that, there really isn't a ton that can cause dips in brightness. That's not like a planet or like a binary star. For other types of stars, specifically really young stars, there are people that study these objects called dipper stars, which they get these sort of semi-periodic dips in brightness that have really weird shapes. And for a while, people didn't know what it was. I think that the best sort of hypothesis right now is that it's a very young system, and so there's still a lot of like gas and dust around the star, and that this gas and dust sort of sometimes blocks the star and then sometimes doesn't, and so you get a semi-periodic thing happening. Yeah, that would be, I would say, the weirdest thing that people are still trying to figure out. But other than that, like it's fairly straightforward to tell what the dipping is due to by looking at the shape of the dip and the periodicity of it. Yeah.
Well, glad there are no A-type stars in the room, because you just called them simple. Just kidding. So how far out can tests detect a planet?
Right. So a vast majority of the planets that tests will find will have orbital periods shorter than 10 days, which corresponds to like somewhere between a fifth and a 10th of an AU. So like take the distance between the Earth and the sun and then divide it by like 10 to 20. So we're talking about planets that are really close to their stars. And that just has to do with the fact that these closer stars are more likely to transit, and so they're easier to find.
Great. Okay, I had to read this question, but it's a good one too. I was like, what? Okay, so if the signal for determining the existence of a planet is determined by the orientation of the star system, it must be on the edge to our sight line. How many percent or fraction of the Milky Way star systems have this favorable orientation where we can actually detect the planets by the spectral shift or occultation versus who don't have that kind of precise location orientation?
Right. So it sort of building off my last answer, it depends on how close the planet is to the star. So if you have like a star is here and you have a disk that's inclined like this, or the planets are all sort of orbiting along this plane, you'll be able to detect the ones that are really close, but the ones that are really far are like up here. And so they won't be going in front of the star from our perspective.
Okay.
And so if we're talking just planets that are really close to their stars, like less than 10 days, it's something like 10 to 25% of stars should have planets transiting them if there are planets there. And so that's also part of the calculation. What goes into the calculation of determining how common planets are is saying, like, if all stars have a planet at a period of less than 10 days, but only 25% of stars are oriented such that we would be able to find them, then we can use that to determine, like, what is the intrinsic frequency of planets, essentially.
Got it. That makes sense. All right, great. Okay, I'm going to hand things back over to Jen.
Awesome. Thanks, Dee. I love the questions. Keep them coming. You're asking great ones. So here's a question for Satya. How accurate can you be in your measurements of quasars in space? Is there much of a margin of error?
So it's hard to quantify how precise when we're dealing with such big units. But the big difference I want to make is the precision in the methods that we're employing, because the precision actually doesn't really depend if we're looking at a galaxy or a quasar. It really depends on the methods that we're using. So if we're using photometry, meaning taking, regular pictures and trying to figure out from this what the distance is of a quasar, it's going to work well enough. But then if you want to improve by an order of magnitude, meaning if you want to do 10 times better, then you're going to want to use the other methods. This is the method that I'm using for work, is called spectroscopy. And this is when you, instead of getting a picture of a quasar, you're getting its spectrum, meaning you're counting how many photons of which color. And if you can get how many photons of which color, it also actually tells you very precisely what's in the mix, what's in the quasar, what are the chemical species. And from that, you have, from atomic physics, very, very, very precise references that will give you, allow you to make a distance measurement that is, again, 10 times better than if you were just taking a regular picture. So yeah, so it. Very well.
Okay, thanks. That's a good explanation. I think your previous answer might sort of relate well to this next question, which, how large is a quasar in comparison to a galaxy, by the way?
So because a quasar has something very heavy in the middle, right? A supermassive black hole, and that everything that is making the quasar is falling towards that. And in relation to that, quasars are very compact. So if you want to say that a quasar is on the order of, we'll talk in light years, 1 or 2 light years, then a galaxy might be 3,000 to 300,000 light years across every time. And so galaxies are, fuzzier things. And actually also maybe, but that will take more space, but fuzzier. Quasars are incredibly dense objects. And so they will be like teeny tiny, but send all the light.
Got it. So speaking of sort of the density or the mass of quasars, and maybe this is a question for both you and Stephen, what's the mass of a quasar relative to a star?
So Stephen can correct me, but my number that I have in mind is that for a quasar, it's going to range between 3 and 10 times the mass of our sun. And then, yeah, I don't know if you want to correct that maybe, but.
I don't actually know much about quasars, so I can't add much.
All right. So we'll say that it's about, again, an order of magnitude more than our sun.
Got it. Thank you. And then one more question for you, Satya. Do quasars have a north and south magnetic pole?
They definitely have a magnetic field going around, and so see, this is how you know I'm French. I don't know that we actually call them north and south, but definitely we call them, you know, opposite sides of something. And so, because I don't know, north and south sounds very Earth orientation.
Sure.
But yes, definitely there's a magnetic component with different poles, and you know, a field that is proper to the configuration of the quasar. So I think the simple answer is yes, even though I'm not sure if we call them north and south.
Fair enough. So one more question, and I'm going to sneak my own in here because as one of the hosts, I feel like I get to do that. And then I'll hand things over to Dee. Was our own galaxy once a quasar?
No, it does have a black hole at the center of it, right? Every galaxy has, but it's not supermassive. And so it didn't create this whole dynamic of having everything so brought up to the middle that then it's spewing away. Otherwise, we wouldn't be there to talk about it. So there's a black hole, but not a quasar.
Excellent. And I'm going to ask my question, but it's one we always ask. I want to learn a little bit more about your histories in science and your interest in astronomy and cosmology. So tell us about a little bit more about your career path, because again, we might have some young scientists in the audience who are interested in this study. And I know often, or this type of study, and I know oftentimes people have kind of meandering paths, and it's so interesting to hear how everyone got interested in their line of work. So why don't we start with you, Stephen?
Sure. So I guess I'll say mine's not too interesting. I mean, always as a kid, I would watch like the sort of television programs on Discovery Channel or Science Channel, specifically about exoplanets. So when I was a kid, when I was really young, I was like, oh, that would be really cool to study exoplanets, because it was a very young I mean, still a young field, but I was born in 1995, and that's the year that the first exoplanet was discovered. So sort of growing up, it was like a new, exciting thing, and I sort of wanted to get into it. When I got to around the end of high school to college, I got a little maybe jaded is the word, and I said, like, I don't think that's actually a career path that's reasonable to expect, because I didn't think that astronomers were like that common. Like, I knew that people taught astronomy at universities, but I wasn't sure what the state of the field was like. So I still did physics. I sort of had planned for a few years to go into like particle physics or quantum physics, and then during college, I was just sort of looking at the directory of people to research with, and I found that there were a few people that actually did exoplanet studies. So after striking out many times to get a job in a quantum physics lab, I got a research position working with someone that did exoplanets. And then from there, I was like, oh, I guess this is what I wanted to do from the start. So let's just do this.
I love that astronomy was like your fallback career. That's probably very rare.
Yeah, it kind of worked out that way. But it's good because it's what I wanted from the start. And then now I'm here.
I was gonna say your destiny was written in the stars.
Yeah.
Wah. Satya, what about you?
Before I answer that, I just want to correct. I said solar masses, I meant millions of solar masses when I was talking about the weight of a quasar. But so for me, it's kind of similar to Stephen, as in I knew very young that I was interested in that. And that's mainly because my parents, whenever I would ask questions, would always give me, real answer and help me walk my way through finding things out. So that was really nice. But maybe what about my path can be more interesting for people thinking about, going into STEM and doing whatever they want for their education, is that my family has been awesome. The educational structures I was in were not encouraging whatsoever. And so really, if you're considering doing something for your education, for your career, for your life, something I can tell you is always, take ownership of every choice and every decision that you're going to make, and do not give that up to defer to someone that you think has more authority than you on, would know better. Because at the end of the day, your education, it's really the gift that you're doing for yourself and something that's going to serve you for your entire life. And you're there to learn. So you don't need to be excellent at it from the get-go. The point is that you want to get good at something and you want to go through that learning process. So if really there's something about my, trajectory that I can share with you, is really take ownership of what you want, and don't, defer to other people who don't know you, who don't have to live with the choices that they're going to advise you to take, and really, make a choice and then back it up by putting in the work, for sure. But, take ownership of your education.
100%. That is fantastic advice, Satya, and great advice, really, from both of you. We love it. And that brings us to the end of yet another Midday Science Cafe. So thank you, everybody, for joining us. Before we close, I do want to thank Stephen and Satya one more time for their great presentations and their great answers. And again, our audience is the best. You ask fantastic questions. We love it. And we just appreciate you guys keeping showing up. So as always, if you want to stay up to date on research that's happening at Berkeley Lab and at Science at Cal, you can visit science@cal.berkeley.edu and Berkeley Lab at lbl.gov. We actually just revamped our website, so it is much easier to navigate. We encourage you to check it out. Next month, we're going to be talking about animals. And in the interim, we'd love to have you fill out our survey. Dee's got that slide up on the screen. You can scan that QR code. So with that, let me say thank you, and we'll see you again next time.